Okay, guys, I think people are joining and we're going to start. First, I would like to introduce myself if people don't know me. My name is Sabina and I'm senior statistician for Women Health Research Institute. If you're new to the series, last year we did first part of the series, like more basic statistics. For example, distribution, what is odds ratio, what is p-value. But this series, it will be more like mathematical and statistics because we're actually going to go in a descriptive statistic and some modeling, more serious statistics. And the way I do all my lectures, I'm going to do it the way I understand it. So basically, for parametric or non-parametric test, not so much because it's very basic, but for modeling, I'm going to show you models on the real data and going to walk you step by step and explain what I'm doing and what what decision I'm making, why, so you can learn like in real time how you do models. So in this series, there are several lectures. First is parametric versus non-parametric test. After that, there will be lecture about simple regression as linear and logistic regression. Last statistical section will be about Cox model and survival analysis. And we prepare a series of documents that help you like to develop research question and hypothesis. And the last lecture will be a show off or workshop on those documents. So I'm going to start with my first lecture today. It's called Stat Series, Parametric versus Non-Parametric, the Stat Battle. So the objective of this lecture is to understand foundation, explore key differences between parametric and non-parametric tests, learn about those tests like t-test, ANOVA, Mann-Whitney U-test group, and others, and gain skills how to look on the outputs and how the tests are calculated. And the most important thing is that I learn from talking to students that understands the difference between parametric and non-parametric tests and understand what are assumptions for parametric tests and what violation of the assumption can do to your statistical work. So here is our detective. Rebecca called him Gucci because of his outfit. I don't think we should call him, we can be sued for defamation. But basically, our detective is on the mission. He has a question. Blood pressure is improved due to our exercise. So for this specific situation, if we transfer it to mystery story, our suspect is exercise because it's predictor variable and it's doing something. What is our crimes that causing a significant improvement in blood pressure due to our suspect's work? So our prime suspect in this case will be our null hypothesis. And what is our null hypothesis in this case? There is no significant impact of our predictor variable exercise to our outcome blood pressure. So basically we're saying if we observe any changes in blood pressure due to exercise, it will be by chance only. And the investigation is to understand if there is enough evidence to convict exercise in the crime of improving the blood pressure. And so basically here I'm doing it in more like our detective story in more details. So what we need to do? First, we need to gather evidence. So we need to have some data and analytical plan first. Also, we need to understand, to develop our hypothesis, looking into main suspect. Is exercise a main suspect for causing a significant change in blood pressure? Testing the evidence. How much evidence differ from what we expect if the suspect was innocent? And the p-value will be our tool for checking our alibi to decide if the suspect is guilty or not. Why statistical test is important? Because if we use the wrong test, we actually can convict an innocent person and put it to jail. So for example, if we needed to use non-parametric test and we use parametric, any statistical software will give us results because statistical software and algorithm inside doesn't care about it. But the results of our analysis might be biased because we use the wrong test. So there is two types of tests usually, independent sample test or dependent sample test. Independent samples test where it's test where we have two independent groups. So our hypothesis in this case, or our question in this case can be blood pressure is improved due to exercise. So we have one group of individuals that not exercise a lot or not exercise a lot or regularly, and another group of individuals who engage in regular exercise. And what we're going to do, we're going to compare to those two groups to decide if our question that blood pressure is improved due to exercise is correct. In this case, our null hypothesis will be there is no difference in average blood pressure between individuals who exercise and not. And the average blood pressure of individuals who exercise is significantly lower than those who do not. This will be our alternative hypothesis for this specific test. So now we're going to do paired test, or dependent. So basically, this is classical case that where we measure something before and after. So here we can ask the question, blood pressure is improved due to exercise. So we have a group of people and we want to determine if they exercise for at least 30 minutes a day, if their systolic blood pressure will be low because of the exercise. So basically what we're going to do measure before. They're going to exercise for 30 minutes and sometime after we're going to have another measure. So we're measuring blood pressure of same individual in 2 time points. So what null hypothesis will be in this case? There is no difference in mean systolic blood pressure before and after exercise. And our alternative hypothesis in this case will be exercise reduces the blood pressure. So basically for this specific pair test, what we will be interested in the difference between blood pressure before, after, and before. So first, I'm going to talk on parametric tests. So I'm going to talk about t-test because all of us use it almost on daily basis. And why t-test consider parametric test? Because t-test is built on specific distribution. In this case, it's normal distribution. So non-parametric test will be tests where there is no distribution, there is no parameters, and most of non-parametric tests, it's kind of basic math, and I'm going to show you how to calculate how to do basic math to figure out the answer to our question. So what's most important for parametric tests, there is a lot of assumption. And the problem is if some of your assumptions are not hold or we check our assumption and those are violated, you get the results, but results will be wrong. And I had situations that like I had data, I even didn't check if data is distributed normally or not. I did t-test and I received the results and results were not significant. After that, I checked the distribution and I said, oh, it's really skewed. Let me try non-parametric test. And for non-parametric test, I got completely opposite results. So basically, if you have assumption violated, you might get biased results. And based on this one later, after the descriptive analysis, if you do any statistical analysis, your statistical analysis will be biased because your initial test, only to test in one independent variable and outcome, will be biased already. So for example, in this case later, if you take those 2 variables and adjust the additional characteristic of the person, yes, your adjusted model might give you results that you will not be able to explain just because your first test was done incorrectly. So what are t-test assumptions? And we're talking here about unpaired tests. So basically, we have 2 groups of individuals because for paired test, the assumption will be slightly more loose. So independence of observations. What does it mean? Blood pressure measurements from the 2 groups should be totally independent. Each person's blood pressure in one group must not be influenced by measurements in the other group. So I can give you here an example from real life. I recently did an analysis of if bleeding during early bleeding under 20 weeks and pregnancies can lead on to preterm birth, for example. Yes, initially the data was given to me. I thought it's individual people, but actually it was the birth or pregnancies. So basically here, if I put two people in two different groups, one person can have bleeding in one birth or pregnancy and not to another. And if I will compare those two pregnancies of the same person, those groups are not independent because the outcomes and the outcomes of the pregnancies and characteristic of the person will be similar. Yes, so we need to be sure for unpaired tests that our groups are completely independent and there is no contamination in the data. Example, we randomly selected 30 exercises and 30 not exercises and measuring their blood pressure independently. This will be structure of our design for the specific test. What we need, especially for this test, is that our blood pressure in each of the groups is normally distributed. So a lot of people doing a mistake here. They have like data about all blood pressure. They doing the distribution and looking that it's kind of normal, but it's incorrect. We need to check the assumption for each group specifically. And I personally saw a situation where if you put all data together, it's kind of will be very close to normal. But if you divide those groups, you can see that maybe one group was skewed on the right and another on the left, and together they get normal. So it's very important to check normality for each group individually. And it's why those groups are independent as well. So for example, for unpaired tests, we can say if the group of exercises most systolic blood pressure values are around 120 for those that exercise, with fewer extreme values, forming bell-shaped curve. But for those that not exercise, maybe the distribution of systolic blood pressure will be much different. So, additional assumption for unpaired test is equality of variance. So technically for the classic t-test, the most important thing is that the variance in two groups is almost equal. If the variance is not equal, you still will be able to do the t-test, but your calculations will be done completely on different formulas and completely on different structures. So it's why it's very important to check if the variance is equal. And based on this assumption, you will decide what type of unpaired t-test you're going to use later. So now we're going to pair test. Because it's pair test, actually, the assumption of normality and independence will still need to be checked. But here, again, not all people before and after, all our data set, all our blood pressure measures should be normally distributed. What we need to check here is the difference. So basically, the difference between our blood pressure after and before, it's normally distributed. So, and because we're checking for people before and after, and those are like same people, and for independence, what we need to do the pairs, like our before and after for each individual, independent for our measures for other individual. Yes, so it's a little bit different because of this structure of a pair test. We actually don't need to check anything about the variance. We don't care. So I think it's great, less work for us. So how are we going to check the assumption? For normality distribution, for either paired or unpaired test, the most useful tool is QQ-plot. What is QQ-plot? And I talked about it during my data visualization lecture in more details. Basically, we have quantiles from our data set and quantiles from normal distribution. So on x-axis, we have theoretical quantiles, basically coming from normal distribution. And on y-axis, we'll have quantiles from our data. The red line represents the ideal cases where the data is perfectly followed the normal distribution. So basically, you can see on the left part of the slide is the way the QQ plot looks. It's probably the normal distribution because it's very close on the line. But if we look on the right, it's not normal distribution. So it's really easy graphic visualization that helps us to understand if our difference or our measures for two different groups are normally distributed. Equality of variance in two independent samples can be checked using F-pool test, also known as folded test. So basically, I don't know about R, but if you run analysis of t-test in SAS, the output will show you the statistical test for folded F-test. And based on this one, you will decide which p-value, which t-test p-value you should look, because they will be different for equal variance or unequal variance. So basically what you need to do in any package, there can be different tests. Because I use SAS, I know this test. And basically we need to establish first if our variance of our two groups for unpaired test is similar. So here I put the formula of F-test. It's basically S, where S squared 1 and S squared 2 are sample variance. And the larger variance is always placed in the numerator to ensure F is more than 1. So our null hypothesis in this case will be the variance of two groups are equal. An alternative hypothesis, of course, are not equal. So basically, if in our output we see that our p-value is less than 0.05, we would reject the null hypothesis. And we reject the null hypothesis, we understand that the variance is not equal. So now what we're going to do? Because we established the difference in variance, if it's different or not, we will have two completely different t-test formulas. On the left is the formula for equal variance, and it's like a little bit simple formula. And on the left, we have t-test formula for unequal variance. And actually, you can see that formula for variance on the bottom of the formula is slightly different. So here what is SP? SP in the formula is pooled variance, and here like how you calculate it. Basically, this is a weighted average from our samples variance S1 as S2. And how we going to establish if we accept or reject our null hypothesis in this case? We would need to calculate a critical T value. And how we're going to do it? We're going to do it from a degree of freedom. If you listen to my lecture about p-value, I gave example and I explained what degree of freedom is. Basically, in statistics, it indicates the number of independent values that can vary in an analysis without breaking any constraints, or the number of independent values that a statistical analysis can estimate. So usually for any simple test, the degree of freedom will be n-1 because you lose in 1 degree of freedom, for example, to calculate the mean. And in this specific case, basically, first we're going to calculate our T statistics from our T's value from the formulas, either for equal or unequal variance. We have it on one side. And after that, we're going to use specific formula of degree of freedom to calculate the critical value of t-test. And based on this one, we decide if to reject or accept our null hypothesis. So basically, if our C value from calculation is more than critical value, we will reject the null hypothesis, and opposite. So how are we going to calculate degree of freedom? Here again, why equality of variance is very important, because to calculate our critical T value, we're going to use two different formulas. If the variance is equal, our formula will be very simple. So basically, it's sum of number of people in our two samples minus 2, because we losing 1 degree of freedom for each of the sample. But if our variance is not equal, then we're going to use the Welch-Sutter-White equation for degree of freedom adjustment, and the formula will be different. I put it on the screen if you're interested to look into it. So basically, here's the summary of all what I was talking about until now. We need to check the assumptions of our t-test. We need to decide, first of all, if the distribution of two independent samples or difference is normal. We need to calculate t based on the equality of variance formula. We need to choose appropriate degree of freedom formula, and then we can calculate the critical t value and compare both. So I didn't give example here in details for t-test because any specific program can run it, and you can find online like data sets that are normally distributed or not normally distributed, and play with it and see, or like calculate the formula in the Excel. So I didn't give a detailed example. So now we're going to pair test. So basically here we're measuring something before and after, or in two different time points for same person. One of the good visualization examples here, it's a simple box plot. So basically we measure the blood pressure before exercise and after, and we plotted them using box plot to see what is summary of our distribution, and we can see if there is like difference between blood pressure measured before and after. So here on the left again, I put the formula for t-test, where z hat, it's mean of the differences between paired observation. Mu 0, it's hypothesis mean difference. It's usually 0 because we checking if there is difference or not. There is a standard deviation and number of pairs. And for pair test, the degree of freedom will be n-1. So basically here we're going to do the same. We will calculate the mean before and after for each person. We calculate the mean of differences. We compute the standard deviation of the differences. We compute the t-statistic using formula I put on the left corner. We calculate degree of freedom as a critical t-value. We compare them and we decide if we accept or reject our null hypothesis. So now we're going to go to non-parametric equivalence for those two tests, for paired and unpaired. And my lecture will be mostly concentrated on a non-parametric test because it's less intuitive. And also there's actually conversation with the statistical community what actually non-parametric test is comparing. Because technically, if you look for Wilson rank-sum test, it's actually theoretically comparing medians, basically taking medians of two population kind, and you can compare median. But also non-parametric test in this case can show us if two groups that we're comparing are coming from same or different distribution. Yes, but here is the catch. In non-parametric test, we actually not comparing anything about the sample, coming from the sample. We're doing a rank transformation to our sample for both paired and unpaired tests, and we usually using the transformed data to make our decision about our sample. So we're not using actual values from the sample as for t-test. We need to transform it to something, and based on this transformation, we're going to do some calculation and we make decision of our assumption. In addition, for example, Mann-Whitney test, so it's otherwise called Wilcoxon-Ransom test. Basically, this one actually specific case on logistic ordinal regression with proportionality, but it's not relevant to this series of lecture. I'm probably going to talk about something like this next year. So how basically our non-parametric test works. We rank each score in the sample. We compare the sums of rank between two groups. And based on this one, we can assess whatever the two groups are likely to come from the same population. So what we're going to, we still need to check some VEC assumption for this specific test. Our dependent variable should be measured as ordinal or continuous. So basically our Y in this equation should be continuous, same as for t-test, it's like blood pressure measures, and our independent variable should include only two categories, like male, female, exercise, not exercise. If we have more than two categories, we would need to apply different variation of the specific test. Of course, here, as in anything in statistics, we should have independence of observations, which will mean that there is no relationship between the observation in each group or between the groups themselves. So basically, our measures are, as for t-test, are completely independent. And in this specific case, because test is not non-parametric, we don't care about distribution. We don't care how the distribution looks, if there is outliers, if it's skewed. The only thing we check in here is the distribution coming, if two samples coming from the same distribution. And here I did the graphical visualization, like you see two distribution overlap from two samples mean everything is fine. And on the right, we can see the distribution can be slightly different. So how are we going to do it? So here, basically, I show how we doing the transformation of the data to make it a rank sum. So we have, I did random sample of 20 people, I believe, for groups that exercise and those next not exercising, and I included the systolic blood pressure. So what you do, regardless of the group, we sort the blood pressure from smallest to largest. Yeah, and after that, we rank them. So how we rank them? You can see in the left table that we have two blood pressures as 120. So the order is 1 and 2. So means the rank will be average between 1 and 2, 1.5. We have 122 as order of 3, 4. So the rank will be 3 plus 4 divided by 2, 3.5, and so on. So basically, we took our data, we sorted our blood pressure in order from smallest to largest. We assigned number to each order, and we calculated what is our rank. After the rank is calculated, we're looking for those that exercise or not exercise. It's just summing up the ranks. So if I did the calculation correctly, and I hope I did, you can check me later and let you know. So the rank sum for exercises here will be 88, and for not exercise, 122. So what we're going to do next? Next, same as for t-test, we're going to use a bunch of complicated formulas. I'm not going to spend a lot of time on the slide. You can rewatch it later in our recording, but basically I show here like what are the formulas and how I feed the numbers into the formula to actually calculate the statistics and make my decision about the hypothesis. So for why it's called my Mann-Whitney U-test, because actually we calculating something that called U statistics. And here on the on the left corner, we have the formula that was developed for N statistics. So basically the formula here is very simple. Because there is no distribution, we're using only number of observation in each group, and we're using the rank sum in each group that we calculated previously. For the calculation of U-test, what we're going to do, we're calculating U statistic for exercises and U statistic for not exercises. And I believe that about 2, we're going to use the smallest one. smallest one from the ranks. So after that, using U statistic, we're going to calculate Z statistics, and based on the Z cutoff, we're going to establish if we reject or accept our hypothesis. We all know from the school that Z value for 0.05 is plus minus 1.96. In this specific example, our Z value was minus 1.29, if I calculated it correctly, because minus 1.29 falls between the minus and plus 196. We fail to reject the null hypothesis. So basically, but it doesn't mean anything about the blood pressure, because for null hypothesis, the only thing we can say is there is no enough statistical evidence to prove the difference. Yeah, this is what happened with the null hypothesis. So now the same way we can calculate the parametric test. So the name of the test is sometimes confusing, but non-parametric pair test called actually Wilkinson sign rank test. So, and the way we calculate it, it's very similar to the unpaired test. But here we have a difference. So what we're going to do, we have our measures before and after. We calculate the difference of before and after, and we are taking an absolute value of the difference. Yes. After that, what we're going to do, we have only 10 individuals because we measure the measure for before and after for same individuals. So basically, we calculating difference and non-difference. And what I did here. And I think we are ranking the difference here. We're sorting by difference here. So we calculated the difference and we took the table from the left part of the slide and we are sorting them by the difference, and we're using kind of absolute difference because in this point we don't care if it's negative or positive. So after that, what we're going to do, we order the rank same as we did previously. We put the order number for our sorted data set and we calculating the ranks. And here in the bottom, I actually show how the ranks are calculated. For example, you can see for the difference of 1, we have 5 observations where absolute difference is 1. Yeah, so how we calculating? We calculating the orders 1, 2 plus 3 plus 4, 4 plus 5 plus 6 divided by 5, it's 4. So our rank for difference of 1 will be 4, for difference of 2 will be 7.5, and for difference of 3 will be 9.5. So after that, the same as before, we calculate the rank separately for those negative and those positive. And based on my calculation, it's 11.5 and 42.5. And again, we're using the smaller statistics, so it's called W statistic here. So we're going to use 11.5 for our future calculations. And here I put the formulas for mean and standard deviation of the specific test. And we're going to use those calculations those formulas to make a decision of our final decision based on the with statistic and degree of freedom. So here I plug in the numbers in the formula. So basically I calculated the mean and I calculated the standard deviation, and it's step 2. It's step 2 for formula because we have ties where like difference is equal. We need to do adjustment and correction for ties for our standard deviation, and this is how we're going to do. We have for 1 we have 5 ties, for 2 difference of 2 we have 2 ties, and for difference of 3 we have 2 ties. So here's the formula how to calculate adjustment for the ties, and adjustment for the ties for standard deviation will be 132. So we put everything in the formula, and based on our calculation, our Z value here is minus 4.8. Yes, and based on this statistic, because it's less than minus 196, we reject in this case a null hypothesis. So basically, we have significant change in blood pressure before and after the intervention. So basically, now we can go ahead and say, oh, what will happen if we have more than two groups? So if we have more than two groups, both for parametric and non-parametric tests, we can use additional tests. So basically for parametric tests, when everything is not normally distributed, we can use ANOVA. So basically t-test, it's a special case of ANOVA when you have two groups. For ANOVA, you can have multiple groups, theoretically up to infinity probably, but usually like in statistics, you have 2, 3, maybe 4 groups that you need to compare. So what's important here when you do ANOVA for multiple groups, in addition to calculate the statistic for full ANOVA, yes, we also need to do a pairs comparison. So basically we can use a t-test and to compare all possible combinations of our groups to see if there is difference between several specific groups. For example, we can have 3 groups and our final statistics for 3-way ANOVA will be statistically significant. But it can be that only 2 out of 3 groups are actually very, very statistically different and other not. So we need to check the paired comparison. So for instance, if you want to compare blood pressure among 3 groups, those who exercise, those who take medication for blood pressure, and those that do neither, we would going to use classical 3-way ANOVA. ANOVA allows us to test whatever at least one group mean is significantly different from others. So basically, what I just said, we can run 3-test ANOVA and it will be significant different, but only because one of the groups was really significant different from another 2. It's why we need to do pair comparison when we present ANOVA in the publication. For ANOVA tests, as for t-test, there will be same assumptions, yes, equality of variance, normality, and independence of observations. And if we have not equality of variance, same as for t-test, we can have adjustment for Welsh adjustment, and we can run Welsh ANOVA for unequal variance. For the non-parametric test, the extension of Mann-Whitney U test is Kruskal-Wallis. I hope I pronounce this name correctly. I never do. So basically, same as for t-test and ANOVA, this test is extension of Mann-Whitney test for 3 groups. But methodology of this test is not changing. It's exactly the same. We still doing the ranking and calculating sums, but in addition to 2 groups, we have additional group. And here as well, we don't need proportionality, or we don't need normality assumption, and we don't care about outliers or anything else. And here again, for 3 or 4 groups test, we are checking if our different groups coming from the same or different distribution. And the same as for ANOVA, if you have more than 3 groups, the final test statistic is going to show you will be statistically significant probably if only one of the groups is statistically significant. And here again, you need to go back to Mann-Whitney U test and do pairwise comparison. So, and if we did everything by the book and calculate everything correctly manually or using specific program for R, SAS, STAT, or any other statistical software, as I always say, if we did everything by the book, we probably choose the correct test. And we're probably going to put the correct person in jail, and an innocent person will remain free. So summary of our lecture, basically, whatever I said at the beginning, we're going to talk about, we talked about. So I explained the difference in parametric and non-parametric tests, where parametric tests are based on some kind of distribution. In case of t-test, it's normal distribution, but there are probably a million other tests that assumptions are for different distributions. We explored the condition under which each type of the test is appropriate. So basically, we usually start with t-test when we have like continuous variable and we want to compare two groups. Theoretically, we should start with assumption check for t-test, because if our distribution is normal, we can use t-test based on the variance we decide if we use a classical t-test or adjusted t-test, and we using different statistics to make decision about our hypothesis. And if the data is not normally distributed initially, we can go to non-parametric test. So basically I talked a little bit about this and show you the formulas, and you can go back to slides later in the recorded presentation, or you contact me if you have specific questions about the formulas of how to run the test. And I specifically wanted to show you how Mann-Whitney or test for both paired and unpaired example are calculated just because of transformation. We need to understand really carefully when we make decision on our hypothesis testing using non-parametric tests. Yes, we're not comparing the data from our sample F for t-test. We're doing transformation to ranks, and we're actually calculating the sum of ranks in different ways, and we calculating our statistics based on those ranks, and we decide on our hypothesis testing based on the ranks. And it's very important to understand intuitively because it will help you to understand the results of running the specific test. So, and also I give you a short example how t-test can be transformed to ANOVA for more than two groups, and same for the parametric test. I guess I'm too early, so there's nothing I can say, but because the topic was slightly complicated, we can open the discussion for questions, and you can ask any questions you need. Or you can write it in the chat.
The first question is, how can we check normality?
So first of all, I usually, and I talked about it in my data visualization lecture during summer school or last this summer. So I do everything graphically first. I have set of the graphics that I use to do exploratory analysis on the data before I even go to some tests, because I think it's very important either for normal or any other distribution, parametric or non-parametric, to understand your data. If you don't understand your data, you cannot go to do tests, because you will never be able to understand your results correctly. So as I showed before, so graphically I'm using QQ-plot. Yes, it's a very simple solution how to check for normality. And there are also a bunch of tests that you can run. I know in SAS you can run PROC univariate, and it will give you Kolmogorov-Smirnov statistic for normality. So based on the statistics, you can decide and if distribution is normal or not. There are multiple other tests For normality, I think I forgot the name. There is one for like people suggest to use for smaller sample, less than 30, and other tests for larger sample. But I think when people mention like some for t-test, we usually say, oh, if sample is more than 30, it's probably normally distributed and we can use the t-test. Actually, the 30 is there because when I studied, we didn't have computers and we actually had like t-test books with all the critical values, and we looked on the book, and basically for t-test, they didn't print the book for more than 30. It's only the reason why they say, oh, if it's more than 30, you can use the normal distribution statistics. So yeah, so you check in the QQ plot. So if you have it's not like exactly, but if you QQ plot is very close to the one on the left side, it suggests that it's close to normal, or on the right side where it's really skewed about the line, it's not normal. So I didn't talk about it. Some say you can use like transformation to make it normal. And the most common transformation for your data is log transformation. I personally, as a statistician, I wanted to say, I got distracted. What I was talking about. So about log transformation. So you can do log transformation of your data. Yes, you log transform. So basically you had blood pressure, assuming it's like very skewed to non-normal distribution. You say, oh, I'm going to use log. You log it and it's normal distribution. So what? You feed to your model or comparison the log. So any decision that you're going to do in your model is back on log transform data. So you cannot infer anything about your actual data. Yes, sometimes transformation is very useful. For example, I worked before in area of kidney transplantation and HIV, and in those we measuring viral load of specific virus, CMV virus, HCV virus, HIV virus. Yes, so for the viruses, use normal log transformation of the viral load is very appropriate. Yes, it's very appropriate clinically because in instance saying the viral load was 1 million, you can say, oh, the viral load was 6, it's 10 and 6. Yes, for some of them, it's very good and appropriate, but generally, if you're asking me, I rarely use transformation. The only way when I'm going to use the transformation, it's probably for Bayesian statistic predictive modeling. If something is like, because Bayesian statistic can impute values based on specific priors. So, and it's actually for me to impute the data for specific priors to make the prior feasibly usable. I might consider to put some variables like BMI or age as log, but I usually do it in the cases when those two variables are not so important. I just have them in the model. Yeah, but generally I personally don't suggest you to do transformation unless you really understand how you're going to explain your data to your readers or in the publication.
So another question, this one is from Atul. Thank you so much for submitting. Thanks, Sabina. Since Kruskal-Wallis has the same assumptions as Mann-Whitney, is it okay to use it for 2 groups as well?
Yeah, you can use it. So I personally don't use it. I have macro. Like I don't calculate anything and don't copy paste anything. I have macros. So basically I use SAS, I click the button and I have my output. So what I do, I usually distinguish. So in SAS, for example, if I have 2 groups, I'm going to use Mann-Whitney statistics. And if I use more than 2 groups, I'm going to use Kruskal-Wallis calculated p-value. In most of the cases, those are not different. But as I say, I like to do everything by the book. So in my macro, I actually have 2 codes. I say, or if it's 2 groups, export this statistic for me to final table to presentation or paper, but if more than two, use the other statistics. But I'm not sure about R because I use R only for sophisticated modeling that I think it's hard or more complicated to do in SAS. So then I use R, but for simple statistics, I use SAS, and actually SAS will produce both. If you run simple two-group statistics, SAS will produce your output for Mann-Whitney test p-value and Korsakoff p-value. And most of the cases, they will be very similar, but I think you should use whatever theoretically you should use, in my opinion.
Next question from Stephanie. When we are looking at whether we have equivalent, just more coming in, when we're looking at whether we have equivalent variance between groups, how do we determine if it's close enough or not?
It's not close enough or not. You have a folded F statistics. Let me go back. So you have this folded F test, yes? So it's formula. Like in SAS, when I run a t-test, it's going to show me F statistics, and based on F statistic, I can decide if variance equal or not. You can look on graphically and see if you calculated variance. Yeah, like you distribute. So basically, how you can do, you plot your. You can do a scatter plot for like dots in both groups and see how far away the dots are from imaginary line, or and you can say, oh, it looks like the variance is equal or not. No, you have statistics, and and as far as I know, in R package, basically, I think in R you run package that doing Welsh adjustment to variance as well. It will calculate it will do it automatically if variance kinda is not equal. But I suggest you to do the test and like to check variance statistically. If you reject the null hypothesis, it means that the variance in two groups is not equal and you need to do adjustment. And I have situation if you don't use, like I didn't have a situation, but because SAS output give you both statistics. So basically it doesn't care about your variance. It's because I showed you like formulas for t-test here, equivalent, equal variance and unequal variance. So what SAS is going to do, it's going to calculate variance for both and degree of freedom for both. And it's going to show you statistic for unequal variance, equal variance, and statistic for the variance. And based on the variance assumption, you can decide which p-value you're going to use. And I had situations where the p-values for unequal variance or equal variance t-test were different. So you need to do it very carefully. And I suggest like you can do descriptive analysis and look on your data and plot different things, depends on the packages or your priorities, but you should check variance based on hypothesis. You don't necessarily need to use the folded F test. You can use there's multiple tests for equality of variance. You can use any of them to decide which statistic you're going to use for your paper or presentation or your analysis.
Next question from Ian. Thanks, Sabina. These sessions are always great. If I'm unsure about whether or not some data is paired, is it usually better to default to an unpaired test to play it safe?
No. So this is becoming to something very basic, and I'm going to talk to you about it in my last lecture when I prepare all the documents. We're talking about study protocol or study design. Yes, you need to be sure, like, either you doing the study or you developing the design, like, or developing your protocol for the study, or you have data for someone like me. I don't collect the data. I don't run the study. Yes, but when I receive the data request, the first thing I ask, send me the data request, send me the study protocol, ethics, and all relevant documentation. Why? Because I read it very carefully. And based on study design, I decide what test I'm going to use. So if you're measuring something before and after for the same person, for example, classical examples, they're usually doing it for regression extrapolation is SAT tests or tests at school. Yes, people did the test for SAT. Some of them didn't got high results. They continued and did another course to improve result, and the other group didn't do anything, and you compare into groups. Yeah. So for regression extrapolation, those that didn't do second test after they took course, you extrapolate from the model what would be the expected test. But it's classical example. For example, you were teaching kids math in school. Yes, and after that, you saw oh, the grades are not really good. Maybe they didn't understand, and you come up and show them different approach, like as a game or something like this, and you give them the similar test. Yes, you comparing the results of your test at school before your intervention, before you show them something different, and after. So basically, if a peer test, it's usually measures from the same person or the same group, the same school. Unpaired, it's usually treatment and control group, or two groups from cohort study, as I said, like those women that ever had early bleeding and women that never have had early bleeding for their pregnancies. Thank you.
Awesome. Next question from Bianca. Thanks, Sabina. I usually use GraphPad Prism for my stats as I am not from the field. Usually it automatically recommends tests for my data. Do you know how accurate these recommendations are?
I don't know what GraphPad Prism is, but I think because I know SAS very well and I read documentation only if I need to understand something, because when I use something in R, some package in R or something in R, I usually read the documentation because it's explaining you exactly what it's doing. Yes. So I think maybe I cannot kind of answer the question because I'm not familiar with the specific software, but I think if it's legit software and it's not free and you paid money for it, it should check it correctly. But this is my assumption. It's actually why I read the documentation for R, because R is very cool and it's open source, but you actually need to understand what they're calculating before running the package. I don't need to do it in SAS because if something wrong, you pay for the license, they're responsible to develop the program correctly. So I think if it's a legitimate software and you bought the license for it, it should do assumption for your data properly. Otherwise, you shouldn't pay money.
Those were all the questions.
Cool,
Thanks,
guys.
everyone.
So let's talk about the next lecture. So next lecture, we're going to talk about linear and logistic regression. So you already can sign up. I do both of them in one lecture because actually theoretically logistic regression, it looks like it's more sophisticated, but it's usually much easier to implement that linear regression with bunch of assumptions. It's why I want to put them together, and I use real data. For real data, I ask permission for the people I did analysis for them and for which papers will be published to use that data. So I don't show anything about the data, just the results. But if I want to show some calculations, I'll do some simple example with fake numbers as here to show the calculations. The last lecture for statistics will be my favorite analysis, survival analysis. I come in from the area of demography and we use survival analysis a lot, and also for prediction population as other. It's fascinating. I think it's very simple, but it can give you amazing insight on the data. And basically what I'm going to do, the data set I'm going to use as logistic regression, same data set will be used as continuation for Cox regression because I want to show you what is the difference or there is no difference. It's how it's done. Yeah, thanks. See you in 2 weeks, I believe. Have a nice day, guys.
Thanks, everyone. And yes, the presentation will be shared later.
Shared later, and it will be in, they have like YouTube channel for all my statistical lectures. So basically, there's 4 lectures that included, and also I have, like, if you're not familiar with statistics, my first 2 lectures for Lunch and Learn, like how to prepare and explore your data, basically data cycle, garbage in, garbage out. So and I talk about how I work with the data and how I prepare data personally. And then other one is more philosophical, how I understand statistics in terms of philosophy, what is statistics and what is a probability and what is uncertainty. I really recommend you to listen to the lectures for the next one we're going to do, because a lot of information is continuing and relevant. Thanks.
Thanks.